Good afternoon, everyone. My name is Nicole Olson, and I will be helping facilitate today's webinar, Retrofitting Laboratories, hosted by Antech Controls. This webinar is being recorded. If you are having any issues with the audio, please call in using the phone information on the toolbar. This live webinar is accredited for 1 professional development hour. After the event, all those who have attended the live webinar session will receive an email with a link to request the PDH credit within 24 hours. Questions can be submitted anytime throughout the presentation using the chat or question function located on the toolbar. We would also like to remind you that there is no cost or cancellation fee associated with attending the webinar. The presenter today is Christine Banga. Christine is the Design Project Coordinator at Antech Controls. She has a Bachelor of Science in Mechanical Engineering and has worked at Antech Controls for over 3 years. Today's webinar will go over how retrofitting laboratories is a cost-effective solution to turning outdated laboratories into efficient, up-to-date labs. There are many reasons to consider retrofitting an existing lab. These include updating controls, improving the performance of equipment, and reducing operational costs. Throughout today's webinar, participants will learn what to keep and what to replace during a retrofit project, what affects design decisions, and cost savings associated with retrofitting a lab space. The objective of today's webinar includes being able to determine if a lab should be updated, being able to decide on which equipment is going to be replaced in the lab and how that affects other equipment serving the space, and being able to determine the payback period for a lab retrofit. I would now like to introduce you to the presenter, Christine Banga.
Thank you, Nicole. So to start, I'll just go over the table of contents here. First, we'll start off with reasons why you may want to start or consider a retrofit project. Then we'll move on to the design considerations. So you've decided that you want to do a retrofit, what now needs to be considered. And then we will finish off with a case study where we'll do a cost comparison of replacing entire valve assemblies versus just replacing the controls for an existing lab, for a typical lab. So why retrofit? And I'll start by explaining what I mean by retrofit. That's going in and updating or replacing any equipment in the lab space. So it could be in the space or serving the space. That's all within the scope of this Retrofitting Laboratories project. So a couple of reasons why you would want to consider or may have to do a lab update would be, the first one would be if your controls have gone obsolete or end of life. So venturi valve technology is known to last up to 20 plus years in the field. It's been market proven. Venturi valves are essentially maintenance free and they're very robust mechanical designs. So if they've been properly selected and if the coating has been properly selected, then they will last that long in the field, over 20 years. In that time, though, there's a very good chance that the controls serving that valve are going to go end of life. For older style of controls, so analog controls with very limited functionality, if one of your goals for a retrofit project was for better visibility of the lab over the building management system, analog controls can't facilitate that connection. So you would need to upgrade those to new controls in order to integrate with the BMS. Another reason why you may want to consider a retrofit project would be to replace older style pneumatic actuators. And a pneumatic actuator, I have a picture here. It's this black cylinder on the top right. That's a pneumatic actuator. So with these come higher maintenance costs, just because of the type of technology. And because they are an older style, there is less and less field experience available out there to maintain these types of actuators. And similarly with the controls, with it being an older style, parts, you may run into the same problem of parts going end of life. I have this number at the bottom of the slide here. There are over 750,000 fume hoods already installed in the US. So it's a very large number. And there are many of those fume hoods that do have older style of controls or actuators. So there is a large opportunity in the US to go in and update these controls for better control overall and potentially better visibility over the building network. The third reason why you may want to consider a retrofit project, and the one I'm going to hit home the most on today, is energy savings. I have a few facts here. Looking at the first one, typical fume hoods in laboratories can consume the energy equivalent to 4 American households annually. This seems like a very large number, but if you think about fume hoods and how they themselves require a lot of ventilation in order to maintain safe containment, and all of that air isn't being recirculated back into the lab, it's being dumped directly outside. So because these fume hoods require so much air to maintain safety, and because in the space itself needs to be tempered and the temperature in there controlled in order for comfort for the lab users, all of that energy that's being put into tempering the space that the hood just dumps directly outside, that's all directly related to the energy usage of the fume hood. So that's where that number can come from, of it equaling up to 4 American households annually in energy consumption. So the second point here, closing a modern hood sash can save up to 75% of that energy with the VAV hood. VAV hood, or variable air volume hoods, are hoods where when you move the sash, the air valve serving that hood will open or close to let more or less air through the valve in order to maintain that safe feet per minute or face velocity through the sash opening. What we're comparing it to here would be a constant volume or a bypass hood, where rather than the air valve compensating for that change in sash height, there's a bypass that lets more or less air flow through it when the sash is opened. So you can tell from that description that constant volume hoods may not be the most efficient option and can actually be very inefficient. They do make sense in certain cases. Those cases are when the lab is thermally driven or ventilation driven, meaning that the supply is the one determining the air change rate. In labs where the fume hoods are governing that air change rate, so they're fume hood driven, then it makes sense to go with a VAV hood, because if the hood is not in use, you can turn it down and that won't inflate your supply any more than it needs to be, and then it can go into a state where it's doing thermal control. So CV hoods do make sense in those specific cases because they do have a cheaper upfront cost, but in most cases where the labs are fume hood driven, a VAV hood is what you want to go with. Otherwise, you're going to be having a lot of excess of ventilation in those spaces. The third point here, only 67% of fume hoods in the US are using VAV solutions. And I put in that number again at the bottom there. There are over 750,000 fume hoods installed across the US. And if only 33% of those fume hoods are using are using a constant volume solution, and if 75% of that energy can be recovered back by switching to a VAV solution, then that just shows you that there's an enormous opportunity across the US for significant energy savings, and that can be accomplished by going back and seeing what hoods can be replaced in existing labs and doing these retrofit projects. So I put together this diagram here to show you kind of what drives the cost of operating a fume hood. And I'm focusing on the fume hood portion of a lab space because of this number at the bottom here. Fume hoods account for 60% of the energy used in labs. So they do account for the majority of the energy consumption. And if one of your goals is energy savings for a lab, then you will want to focus on fume hoods as that will be a huge portion of that opportunity. So a couple things drive the operational cost of a fume hood. First would be the ventilation requirements of the hood itself. And then, as I mentioned before, the amount of exhausted tempered air that goes through those hoods, that energy is also directly related to that hood. So for hood ACH requirements, what things affect this number would be the size of the hood. So if there's a larger hood, you would need more air in order to maintain the ACH requirements. The types of chemicals being used in the hood. So if you have something that is of a higher concentration, or if you're doing tests with flammable chemicals in the hood, that might drive up your ACH requirements for that hood, your air change rate requirements. And then also your hood performance. So if your hood requires a higher feet per minute or face velocity in order to maintain safe containment, then that would also drive up the overall air that's flowing through that hood as well. Moving on to what drives the amount of exhausted tempered air up, that is directly related to your geographical location due to the loads from the weather, and as well, this would also affect your energy prices, so your cost per CFM. The lab size and ACH would determine how much air gets exhausted through the fume hood. Also, the number of lab users and instruments in the space would add to the heat loads in the space and can drive up that number. If there's an option, whether or not there's an option to go back into a setback mode. So if your lab has just one constant volume for the supply and doesn't have the ability to turn down when the thermal demands are met or when the lab is not occupied, then that would also drive up the amount of exhausted tempered air through that space. And finally, this last bubble here, the sash open time, the percentage of time that the sash is open. And I put this note here, VAV only. So it would only be a variable with VAV hoods, because CV hoods would just constantly be exhausting the air no matter what. But so sash management, it does play a huge role in how effective your VAV solutions are. So I presented the energy savings that can be afforded by doing a retrofit project and by switching from a constant volume hood to a VAV solution. And the natural next question would be, what is the payback, or how can I calculate the payback for this type of project? And there's actually a nice tool that Berkeley Labs has put together where it takes your different variables such as your geographical location and it makes assumptions about energy prices. You can put in different parameters for your hood dimensions as well as hours of operation. And it calculates a flow rate for the hood, as well as it calculates the total cost to run that hood per year and the cost per CFM. So for my example, I'm going to be using a certain CFM flow rate as the minimum, and I grabbed that from the ANSI Z 9.5 section 3.3.2. It states, as an example, for a hood air change rate between 150 and 375, and based on the hood dimensions, that's how I got my minimum CFM. So in this example, this is the example of a constant volume hood. So you'll have, what I've put in the parameters here is a 5-foot wide hood being run 24 hours a day with a sash open height of 18 inches. That came out to about 750 CFM for the flow rate. And I didn't change this sash height because it would affect the CFM output, but we can say for the CV example, we know that it's always going to be exhausting 750 CFM. And then the total cost per hood came out to run this hood per year would be $2,500. So in this second page, I've put in the sash height in inches that would give me my calculated minimum flow rate that I need to when this hood is in its minimum position. So that ended up being 150 CFM. So you can see that if we use hood 1 as the CV hood example, that it would be always exhausting 750, and that would be a total cost per year of $2,500. But if we were able to close and vary that CFM through the hood, that it can save us it can go down to $500 per year. So I know that this isn't a really realistic example exactly, because we're not going to have our hood closed 100% of the time. So if I've made some assumptions on how the sash open percentage time. So taking those numbers from the calculator, if it was open 100% of the time, that would equal a cost of $2,500 per year. If the sash was closed 100% of the time, that would equal operational cost of $500 per year. But then if we assume that the hood is open 8 hours daily, so 33% of the time, that comes out to around 1180 per year. So we went down from 2500 to 1180 by swapping out our constant volume hood with a hood that could turn down when the sash is being closed. So that afforded us 53% savings by swapping to a VAV hood for this example. And I mentioned it before, but I want to mention it again, that better sash management would increase the savings per year with the VAV system. So if we cut this number in half, so rather than it being the sash being open 8 hours every day of the year, it's open 4 hours every day of the year. So better sash management in this case, when the hood is not being used. That drives the operational cost down further to $845 per year. So again, we went from $2,500 to $845, and that afforded us 67% savings by just reducing the sash open percentage time with a VAV hood. So you can see that 75% energy recovery that I mentioned a few slides before, that better sash management would drive this number closer to that. Some other contributors to energy waste in labs could be too many hoods. So if your lab is too fume hood dense unnecessarily, and maybe people aren't using the hoods for an actual test spaces, maybe they're just using them for storage, that's an opportunity to swap that out for more efficient equipment, a cabinet for example. Hoods, if the hoods have too large of a bypass, requiring more air than really necessary to flow through, that would also lead to excess ventilation. And all of these are related to ventilation. So that's where we're going to focus on. And then air change rate. If the air change rate is set too high unnecessarily, then that would also lead to wasted energy in labs. If your offset is too high in the room, that would indicate that your room has a high leakage rate. So you can go in and touch up the space as much as possible in order to try and decrease your required offset to maintain that safe pressurization. If your duct pressure is too high, that would also inflate these energy costs, and that is one that you could go in and try to see if you could reduce that duct pressure without having to replace any mechanical assemblies. The thing you want to be careful with here is that venturi valves specifically, they require a certain operation, a pressure range in order to operate and maintain their flow accuracy. So if you're turning down the duct pressure, just ensure that all of your equipment is still within its operating pressure range. And then other contributors would be inefficient equipment such as hoods or fans. And then again, if you were stuck with a constant volume supply, so if you had no way of adjusting the supply once thermal demands are met down to minimum ACH in the room, or if the room is not occupied, if it's in an unoccupied state, maybe after hours, if you don't have a means of turning down that supply, then that would be constantly exhausting the same amount of air unnecessarily. So these are all, this list isn't all-inclusive by no means, but these are just a few other things to consider if your goal is energy savings for a retrofit project. So we went over the reasons why you may want to consider a retrofit project, and let's say you've decided that you're going to go with a retrofit project, and now the next question would be, what do I all need to consider when walking through these spaces? What do I need to know? So things you want to look at, and the main question you want to solve by doing a walkthrough of these spaces is, what is the condition of the existing room infrastructure? I've broken it down into 3 main areas. First would be ventilation equipment, so things in the room such as the fume hoods, snorkels, and the fans that serve the lab as well. Next would be the quality of the room construction, so windows, doors, ceilings, all those things, any entry point into the room if there's a chance for leakage. And then the room and air valve control, so the valves controlling the hoods, the controllers that are controlling the valves, and then the controllers that determine the sequencing for the entire lab as well. So those are all, when I talk about controls, that's all those things. So before starting an investigation, best practice would be to gather as much information as possible about the current system. Any information, it may seem like it might not be important at the time, but any information you have about these spaces before starting the project will be a great asset. So not only the original plans, but the as-built as well, renovation details, if there's any major renovations done to the building or the lab spaces in the past, because these labs would have existed for probably a few years now, and you would want to know what all of the changes were to those spaces before starting another change. Wiring information is a big one. I'll go over it in more detail in the case study later on, but wiring information, if you can reuse a lot of the wires that are already existing and you don't have to rerun any wires through the building, that would be a huge time saver. And that would depend on what type of controls you're swapping it with, but wiring information is a big one. And then the current scheduling. So if there were any changes to the equipment in the space that would affect your scheduling, so you want to know what the lab is currently doing and how it's currently operating. Before starting, you also want to understand which goals you are trying to achieve through this retrofit project. Some examples of goals would be improving safety, thermal comfort, energy savings, as I talked about in the previous section, but also some goals might be monitoring and autonomy. Maybe the building staff or the facility staff would like better visibility over these spaces or would like to control them from a central location, and maybe they want better autonomy to be able to change set points without having to bring in different groups. So these are all types of goals that you may want to consider and look at, so that you can strategically focus on different portions of the lab and not have to replace more than you really need to in order to accomplish these things. So the ventilation equipment. Ventilation equipment could include, like I said before, the fume hoods, snorkels, biosafety cabinets, and the fans. And the question you want to answer is the performance still acceptable? A great indicator as to whether or not the performance is still okay for the end users would be just talking to them and seeing if there's anything that they complain about. Is something broken? Is something really noisy? Is something not operating as they think it should? This is all feedback that you can get directly from the lab users. You can also do performance testing to determine whether or not the hoods and the other equipment in the space is operating as originally intended, or if the performance has degraded over time. So, for example, how much CFM are the hoods using versus what they're rated for? If it's using more, that would indicate that there's some increase in leakage area somewhere in the hood, and making it less and less efficient over the years, and that would drive up your energy usage for the whole lab. Other things to consider when looking at the ventilation equipment is, are the uses or the users of the fume hoods changing? So if the uses of the fume hood is changing, if there are different chemicals being or different tests being done in the same hoods as before, you want to make sure that the coating for the valves and that the duct material is still appropriate for what's going on in those hoods. You want to make sure that the new types of tests, whatever they may be, that they're not going to be damaging anything upstream. And if the users of the fume hood lab are changing, you actually might want to consider if the hoods are still necessary for different tests, different lab staff, and you might have an opportunity to upgrade or downgrade the size of the hoods or add more hoods if that's required. So if the number of hoods is changing, you want to make sure that the valve sizes serving those hoods are still appropriate, and that the fan capacities are able to handle those changes down the line. So basically, if you're updating anything in the room, so the hoods, the snorkels, the cabinets, you want to make sure that the things serving those equipment, the valves themselves and the fan, that they're all still going to be capable and that they don't need to be upgraded. One thing to note is that if you're switching to a VAV hood from a CV hood, then a VAV airflow device is required. So for this hood, for example, if they were going to switch it to a VAV hood, whatever's serving this fume hood, whether that's just a constant volume fan or if it's a constant volume venturi valve, whatever it is, it would have to be replaced with one that has VAV capabilities, so the ability to open or close or change set points depending on the sash height. And again, if you're changing to a VAV system, you want to make sure that your fan is going to be able to accommodate those VAV valves. Again, for venturi valves, they need to operate within a specific pressure range. And that would have to be, you'd have to make sure your fan capacity is still appropriate. So next area for consideration for these lab retrofit spaces would be what is the condition of the room? So the construction of the windows, the walls, the ceilings, and the doors. Are there cracks in any of the walls? Are the ceiling tiles not put back properly? Are they cracked? Are they missing? Are the door seals degraded? Do they need to be replaced? So all of these are questions that you can just see visually when you walk into the space and do your walkthrough. And what we're really trying to make sure of here is, can the room maintain pressurization? So the way that you can measure the room pressure, if you don't have a pressure monitor that's permanently installed, you just need a pressure measuring tool such as a manometer, and you would measure one side into the room and one side into the hallway. Maybe you put the hose under the door, and then that will give you your room pressurization. And you can tell if it's what it needs to be, if it's the target, or if it's significantly less or close enough. If it is not high enough, then the room may need to be tightened up, or the room offset may need to be increased. So if there's nothing you can do to tighten up the room, then you will have to increase your room offset. And you want to make sure that if you're adjusting the set points of the supply or the exhaust or both, that the fans have capacity to accommodate those changes. So if you're wondering if there's a way to calculate your room leakage, there is. You can calculate the room leakage area using this equation from the ASHRAE Laboratory Design Guide, Chapter 11. And I'll go over the imperial one here quickly. This volumetric flow rate, that's this V symbol, that is referring to your offset. So if your lab is running at a negative 200 CFM offset, your number here would be 200. Again, I mentioned that you can measure the pressure differential in the room. So whatever you measure, you would plug into this equation here. And then you know your density and your constant, and you can solve for the area. If you wanted to determine what your offset needs to be for a different target pressure, you could plug in back these values and get your offset. This is a very mathematical way of approaching this problem. You can also alternatively just iteratively try to increase your offset in the space and then measure the pressure, increase it again, measure the pressure to get you where your target is, where you want your pressure to be. So this image is just a plot of that equation from the previous slide, plotted at different differential pressures. So for example, if you are targeting a 0.05 inch water column room differential pressure, and you had a half a foot squared of leakage area in that space, then that would mean you would need about 900 CFM offset in order to achieve that pressure. So that's just how that relationship works. Again, you could do it the mathematical approach, or you could do trial and error. Both work great. The last area to consider here is the valve airflow controls and the room controls as well. Are you considering upgrading to VAV controls? If you are, you not only have the opportunity to update the hoods to VAV controls, but you could update everything in the space, so snorkels as well. These typically go on a 2-position switch, so you can have a button on the wall that you press and it opens to its in-use CFM, and then when it turns off, it goes to a minimum CFM, or even a shut-off position. Cabinets as well, and then you can upgrade your lab supply and exhaust if you wanted to have VAV heating or cooling in the space, or that setback mode, and if you wanted your general exhaust to compensate for your fume hood movements, so that your supply doesn't have to be constantly adjusting to follow your fume hoods in the space. So you can upgrade all the equipment or all the valves for the equipment to VAV controls. It's not just the hoods. And then again, from the beginning, a reason why you may want to consider updating controls would be if the controls have gone end of life, or if they're faulty and aren't supported anymore on existing VAV airflow devices. So if you already have venturi valves in your space, they're most likely still operational and still mechanically fine, but you have the opportunity to update just the controls on those devices. So some considerations when you're updating the VAV valves controls: you want to make sure that the size of the valve is still acceptable. So if the fume hood isn't changing, this is most likely still okay. Or it would depend on if the uses in the fume hood are changing as well. If your airflow rates aren't changing, your size is probably still acceptable. And then you also want to know what condition the valves are in. Do they need to be replaced, or can they be reused? So that was the end of the design considerations section. So we went over why you may want to retrofit or consider a retrofit project. Then we decided that we wanted to do a retrofit and we wanted to know what we all had to consider. Now, say for this example, we've decided that we want to replace just the valve controls. Everything else is going to stay the same. Fume hoods, all the equipment in the space is going to stay the same. We just want to update the air valve controls. This case study is going to show the difference between doing an entire valve replacement versus doing a controls retrofit. So specifically, it's going to be showing replacing the entire valve or replacing this controls assembly on the right-hand side here, replacing the enclosure on the valve with something like that. So I mentioned before, you want to make sure that your valve is still in good working condition before deciding whether or not you can do a controls retrofit or if you have to go with the valve replacement. Some things to look for would be, one would be if the potentiometer is still functional. So if you're not sure what a potentiometer is, it's this image here. It's just a variable resistor that gives you position feedback. So when this rotates, it changes the output here, which is fed back to the controller, and that's how you know your position, which essentially gives you your airflow. So for venturi valves, just to dive into this further, the potentiometer would be around here for a venturi valve, and it would be attached mechanically to this control arm. So when this rotates, your potentiometer rotates, and that's how you get your position feedback, which gives you your flow feedback. So you can tell that this is a very critical part of the venturi valve assembly. So if you suspect that there's something wrong with the potentiometer, you need to determine whether or not it's still functional. The way that you can do that is just by measuring the voltage. So you can measure the voltage across the pins, and if it's not zero, or if it's not the excitation voltage, if it varies with movement of the potentiometer when it rotates, then you're probably good to go. If you see visible signs of condensation or corrosion around this device, it may need to be replaced. Another thing you may want to confirm is if the valve still can maintain its pressure independence. So I mentioned before that venturi valves last many, many years in the field, but if they are operating outside of their intended range, so if there's condensation inside of the valve, that could expedite corrosion, or if the valve coating isn't selected properly, or maybe it was, but the uses of the fume hood changed over the years, and the valve coating wasn't reconsidered, then that could lead to damage of the internal parts, and it could lead to loss of accuracy. So if you wanted to determine, if you suspect that there's anything wrong with the accuracy of the airflow, you can measure and confirm by measuring the airflow through the hood. And then you can change something in the system by opening or closing another hood and seeing if that flow is maintained or if it changes, because it shouldn't, right? So that's one thing you could check as well. And then overall, you just want to make sure that the valve body doesn't show any signs of corrosion outside of the valve, because if there's corrosion outside, there is definitely corrosion on the inside where it's exposed to those chemicals. Again, if there's condensation in the valve, so if it's in a place where it's not tempered, if it's too cold, then that could expedite corrosion. So these things, they're not very common, but I just wanted to go over them because if you do suspect that there's something wrong, you can check for them and determine whether or not you can still use the valve or if you can go with the controls replacement. And then I just wanted to make it very clear that these types of controls retrofits can be done for potentiometer-based position feedback, mechanically pressure-independent airflow devices. I know that's a lot of descriptors, but essentially that means Venturi valves. So you can do a controls retrofit on Venturi valves that use potentiometers. So now I'll jump into this case study. So for the lab size, I chose 10,000 feet cubed, and that where the airflows came out to, that ended up being an air change rate of 14 ACH. So I've assumed that this lab is not thermally driven or ventilation driven. I've assumed that it's fume hood driven. So the size and dimension of the fume hoods is what determined the airflow rates. So in this specific case study, there are 6 valves in total, 1 supply, 1 general exhaust, and 4 identical fume hoods that are 4 foot wide with an 18-inch work height. So again, this is a cost analysis between replacing the entire valve assembly versus just replacing the controls portion and reusing the mechanical assembly. Here is the truth table that came out of the hood sizes. I've chosen a negative 200 offset, and then this is what the air change rate came out to. So if you have any more questions about how I put this together, feel free to leave a question or comment. So for this case study cost analysis, I've broken it out into 2 sections, the labor costs and the material costs. And I'm gonna start with the labor costs. And what I've done here is I've broken it out into different areas for cost considerations for both the valve replacement and the controls retrofit. So starting with the valve replacement and starting with the wiring costs, I've assumed that no new wires need to be run. So, as I mentioned before, knowing what wiring is pre-existing and where it's going throughout the building, that would play into this in a large way, because if you are able to reuse a lot of the terminations that are already existing, or maybe there's extra wire run, just exactly for this reason, if you know that it's there, then you can save a lot of time and effort and additional costs for the wiring by not having to run new wires. So that's definitely something that you want to gather information about ahead of time in order to save a lot of effort and time and cost during the install. So in this case, for the wiring, the only wiring that is involved here would be the termination at each valve. So that would be undoing the wires from the old controls, and then after the valve is replaced, re-terminating the wires at the new controls. So that was estimated at about half an hour per valve. For 6 valves, that came out to 3 hours. The next area would be special handling and install of the sheet metal parts. So special handling would be because these valves are exposed to chemicals, the fume hood valves anyways. Because they're exposed to chemicals, depending on the type of chemical, you may need special equipment or special parties to be involved during the replacement. So maybe health and safety or a very specific contractor to do this work. That can play a part in it. Also, because these valves are in existing buildings, sometimes it can be hard to access them in the ceilings depending on what's all installed in the space. So overcoming any of those issues, and you may also need to remove part of the ceiling, remove some T-grid in order to actually take out those valves. So I've estimated this work to be about 3 hours per valve. So to break it down further, that's about 1.5 hours for 2 people to go in and take out the old one and put in the new one. So 3 hours per valve for 6 valves. That came to 18 hours. Then commissioning and balancing. It would take the controls technician about 2 hours to commission the new controls and the entire room. And then 4 hours would be spent with test and balance, verifying all the flow set points. So I've added in this logistics section here. I didn't put any costs associated with this, but I wanted to bring it up because it's something to think about when doing a retrofit project, because these buildings are already up and running. With doing a valve replacement, the air will have to be turned off to these spaces in order to do the swap. So, and I know it's not typically the case where you can shut down air to specific spaces. You may have to shut down the air to multiple labs at once, or even an entire floor at once, and then it's just logistically a little bit more complicated to work out with the building owners and the facility staff and actually the lab users in order to schedule a time where you can shut down multiple labs at once and then get in there and do all these replacements. So overall, the hours for the valve replacement for this specific lab with the 6 valves came out to 31 hours. Moving on to the controls retrofit. For this one, rather than having the wiring and the special handling or the sheet metal parts install separate, I put them all into one category with the added process of calibration. So calibration, venturi valves, when they're in the factory at the manufacturer, they're all airflow tested, and then a flow curve or a flow map is created that is the potentiometer position to the airflow. So that very specific and unique curve for each valve the valve itself is calibrated to that flow curve by the calibration techs at the manufacturer. So when you're doing this type of swap in the field, you're going to have to do that on site. With that assembly, it comes with the new actuator, the new controls, but it also comes with a set of linkage. So that linkage is preset as close as possible in the factory, but there will always have to be some adjustments because not all valves are exactly the same that are already existing in the field. But if you know the size, then it's as close as possible from the manufacturer. So, and the advantage here is that because you're not, all the wiring is low voltage and you're not taking out an entire mechanical assembly, this can all be done by one person. So the install, the wiring, and the calibration, all done by one person. And there is a learning curve that comes with doing this for the first time because of this calibration portion of the work. But once that's overcome, then it ends up being a bit quicker. And for the whole lab, I've estimated that at 6 hours for the whole lab. So for all 6 valves. And again, that's assuming that no new wires need to be run, that there were already enough wires existing in the building. And then controls and balancing. The controls, it's the same as the valve replacement. So again, 2 hours to commission the new controls, and then 4 hours spent with the test and balance. So logistically, I put this section in here again. I didn't put any cost, but it's nice to know that you don't actually need to shut down the air when you're doing these retrofit swaps, when you're installing these kits. In some cases, you actually might need the airflow in order to verify the calibration in the calibration phase. So you don't need to shut down the air, and actually you can do it lab by lab. So what's nice about this is one job that I've heard of that did a retrofit project, they planned it so that it would go on through Friday and Saturday. So they only had to coordinate with the lab users that they would not be able to use the lab on Friday, and that they could come in on Monday and the lab would be done. It would be up and running again. So I thought that was very convenient, and logistically it's a lot easier to plan with the parties involved than doing the valve replacement. So that came out to, for the controls retrofit, 26 hours for this lab space. That ends up being 19% longer in labor hours to replace the entire valve versus replacing the controls retrofit. So this example, it wasn't just to show you the difference in labor hours, it was to show you the difference in processes that are involved with these different types of installs. So if you have any more questions about these control retrofits and what all goes into the work when swapping them, feel free to leave a question or comment. And then the second portion of this cost case study would be the material cost, so the upfront cost of the equipment. So with the valve replacement, you're getting the entire valve assembly. You're also getting brand new controls in this enclosure. And for the fume hoods, keep in mind that you would need to have some sort of coating on here, which would add to the cost. So all those things play into the cost, the upfront cost for these projects. And then for this kit, this is what you would get. And the new controls would either be shipped loose, or if you have it shipped with an enclosure, it would be mounted in the enclosure. So you still get brand new controls with both, just the mechanical assembly is very different. And then here's that linkage that I was talking about for the calibration portion of installing these. So for this specific example with these 6 valves, it came out to be 29% cheaper to use retrofits than replacing and ordering the entire valve assemblies. So that would be weighted differently depending on a few different things for different jobs. But say, for example, if you had a job where the material cost for the valves came out to be $10,000, that would equal, just to put it in dollar amount perspective, that would equal $7,000 in retrofit kits. So significant cost savings up front. And then as we saw with the previous slide, that there was some time savings as well. So again, if you're looking to calculate this for your own specific applications, things that would play into this savings percentage would be the number of valves in the space, the size of the valves, and then the coating that is selected. So just to summarize this presentation, we went over why you may want to retrofit an existing laboratory. It would be to replace end-of-life controls, replace pneumatic actuators, and energy savings. Energy savings being the most significant opportunity available across the US. And then design considerations, we looked at the ventilation equipment, so the equipment in the space, the quality of the room construction, and then the room and air valve controls. And then we also talked about gathering as much information as possible and identifying goals, depending on what you're trying to accomplish in that space. And then we finished with the valve retrofit case study, where it showed that there's significant cost savings in both upfront material costs and in labor costs with going with the retrofit replacement versus replacing the entire mechanical assembly with the new controls. So here are the references that I used if you're looking for more info about where I got those numbers from the beginning. It came from this research paper, which is on SASH management system, and then ANSI Z9.5 and the ASHRAE Laboratory Design Guide. That concludes my presentation. I'd now like to open the floor to any questions.
So we do have a couple questions here. First, Christine, we have a question. How can we retrofit exhaust fans?
Thanks, Nicole. So in the case of an exhaust fan, if you're looking for to improve efficiency, that would be actually just a fan replacement. So you wouldn't update any of the controls for it. The reason why you would want to update the exhaust fan is if it's operating inefficiently or if something down the line changes. So if your fume hood or your valve is changing and you find that you have a capacity issue, then you would need to update it as well. So that would go into the whole project of retrofitting that laboratory space.
Thank you, Christine. Our second question is, For the controls retrofit, how are installation details handled with the control boxes for different manufacturers' models of valves?
So for these controls retrofits, you do have to do a bit more of information gathering up front since you're trying to swap out and reuse what's in this space. So that would just be getting in touch with the rep and the manufacturer to see what details are needed and to make sure that you can put the controls assembly, the retrofit assembly onto a valve. So I think as long as there's a place to mount it, if it's not like a cage rack valve or if it has some place to mount it, then you should be able to put that assembly on the existing VAV device.
Thank you, Christine. That concludes the webinar. Thank you everyone for joining us. As a reminder, you will receive an email with a link to the request the PDH credit and a link to the PDF of these slides within 24 hours. In addition to that, if any more questions come in after the webinar is closed, we will be following up with you. Thank you and have a great day.